Could we raise the Titanic from its tragic watery grave? A century after its legendary sinking, scientists believe the impossible may be possible. From giant inflatable balloons to freezing the wreck with liquid nitrogen, join us as we explore bold, creative ideas for retrieving the iconic Titanic. Number 10. Buoyancy Tanks. The RMS Titanic lies on the ocean floor, over 12,500 feet below the surface of the frigid North Atlantic. This legendary ocean liner met her tragic fate on April 15, 1912, when she collided with an iceberg and sank on her maiden voyage, taking over 1,500 souls with her to a watery grave. Now, over a century later, the Titanic remains lost in the darkness of the deep. But what if we could raise this majestic ship from her resting place and restore her to the surface once more? One ambitious proposal for accomplishing this feat involves the use of buoyancy tanks. Attaching large air-filled containers called buoyancy tanks to the hull of the wreck could provide enough upward force to lift the Titanic off the seabed. This method seems straightforward in theory, but faces monumental challenges in practice. The sheer scale of the Titanic poses the first obstacle. At 882 feet long and weighing over 46,000 tons, the Titanic was the largest movable man-made object in the world at the time of its launch. Lifting something so massive from over 2.5 miles down is an unprecedented engineering challenge. Specialized buoyancy tanks would need to be custom-built to endure the immense pressure at that depth, estimated to be around 5,500 pounds per square inch. That's more than double the pressure in your average car tire. The tanks would need to be forged from incredibly strong materials and rigorously tested before being deployed to the wreck site. Even the air pumped into the tanks would need to be compressed to high pressures to prevent implosion. Distributing the buoyancy evenly across the wreck site is another fundamental challenge. The Titanic is no longer one solid piece. She split in two before sinking. Her bow and stern sections lie about 2,000 feet apart on the seabed. A careful analysis would be needed to determine the number of tanks required and where they must be placed to lift both sections in unison. Otherwise, uneven lifting forces could warp or further break the already fragile wreck. Delivering those tanks to the precise locations necessary and attaching them securely to the wreckage requires its own set of advanced technologies. Remotely operated underwater vehicles would be essential to place each tank, while technical divers would need to bolt them onto the Titanic's hull, and every phase of the operation must be closely monitored. If just one tank detaches, it could throw the entire lift out of balance. Even once attached, the volumes of compressed air required are mind-boggling. Displacing thousands of tons of water will require pumping vast amounts of air into the tanks. This necessitates large surface support vessels to provide the compressed air and a series of durable pipes and pumps running from the surface vessels down to the tanks. Monitoring this complex system from over 12,500 feet above would be yet another challenge. Number 9. Freezing with liquid nitrogen. Ice was the reason for the fall of the Titanic. Can ice be the answer to retrieving its wreck? As wildly ambitious as it sounds, proposals have suggested using liquid nitrogen to completely freeze and encapsulate the Titanic wreckage, enabling its retrieval as a single frozen block. However, generating extreme freezing power poses monumental technical barriers. The concept itself seems deceptively simple. First, create a metal mesh around the wreck to contain it, safeguarding the delicate structure from any potential damage during the freezing process. Then pump enough liquid nitrogen down to the wreck site to rapidly freeze all the water around the Titanic. This flash freezing turns the ship into a solid block of ice that floats upwards as one cohesive unit. However, the realities of achieving this in practice are far more complex. The sheer volume of liquid nitrogen needed boggles the mind. To freeze a site spanning over 1,000 feet across and containing a 46,000-ton ship would require tremendous amounts of liquefied nitrogen gas. Creating a metal mesh around the wreck presents its own set of challenges, including disturbing the delicate ecosystem and the engineering expertise needed to construct a barrier around such a massive and fragile object. It's a feat never achieved before. Delivering these massive quantities 12,500 feet down is the first challenge. Hundreds of insulated tanker trucks would be needed topside just to provide enough liquid nitrogen. Giant cryogenic pumps and miles of specialized pipelines are necessary to push the frigid fluid downwards in a controlled manner and distribute it around the wreck site. Installing such a vast freezing infrastructure on the seafloor is a massive undertaking in itself. Once on site, the near-freezing temperatures and intense pressures found at that extreme depth introduce further problems. Keeping the liquid nitrogen in liquid form as it gets pumped downhole is critical for it to absorb heat and induce freezing. Preventing it from flashing rapidly into gas upon discharge at over 2,500 psi pressure requires custom-engineered nozzles, valves, and flow controls to regulate the cryogenic fluid's exposure to ambient conditions. The ocean's natural thermal insulation also works against rapid freezing. Seawater itself has high thermal mass and conductivity, absorbing tremendous energy before its temperature drops. Generating enough concentrated cooling power to overcome this heat sink effect challenges even the limits of cryogenic technology. Frozen seafloor sediments could also hinder freezing distribution across the wreck site. Monitoring and dynamically adjusting the injection process across a vast area and volume hanging in blackness thousands of feet down is therefore vital. While theoretically possible, delivering such tremendous refrigeration power nearly 3 miles deep beneath the insulating ocean presents technological and logistical barriers as big as the Titanic itself. This literal moonshot freezing method remains confined to the realm of fiction for now, but it captivates the imagination with its vision of raising the legendary liner in one massive block of ice. Number 8. Lifting with magnets. What does a strong magnet do to iron? Attract it. What if we could use magnetism itself to raise parts of the Titanic wreck? By attaching powerful electromagnets to the Titanic's ferrous hull materials, she could be lifted off the bottom using magnetic force. This futuristic method offers a non-contact way to retrieve pieces of the disintegrating liner. However, the realities of implementation, especially at extreme ocean depths, severely diminish its feasibility. The basic premise centers on using large salvage electromagnets to attach to and pull upwards on iron and steel components of the wreck, such as hull plates and structural framing. These water-tightened electromagnets generate powerful magnetic fields when electrical current runs through them. In theory, the magnetic attraction force could provide enough lift to raise some wreck fragments despite their scale and weight. Yet therein lies the first technical barrier: generating magnets with enough raw strength to physically lift multiple-ton pieces of a shipwreck from thousands of feet down. The extreme water pressures and corroded, pitted surfaces down there necessitate magnets with outrageous field strengths and massive power draws. Their electrical cabling must also be super reinforced to avoid rupture when lifting at full power. Additionally, the magnets must be capable of selective attachment and quick release. Randomly grabbing pieces of the Titanic's deteriorating structure could damage fragile remnants or entangle cabling across the debris field. The magnet controller systems must allow for fine detachment and reattachment, even when supporting heavy wreckage upside down in total darkness. This degree of precision control at extreme ocean depths poses its own challenges. There are also risks specific to lifting actual shipwrecks. The Titanic's structural integrity is severely compromised after a century on the seafloor. Magnetic lifting stresses could cause unintended corrosion fractures or even detach rivets and collapse plates. Sudden shifting or collapse of wreck debris while lifted could also snap cabling and bury or entangle the electromagnets. These hazards only intensify the deeper the operation is conducted. The concept of surgically lifting pieces of the Titanic wreck using selectively applied magnetic force is genuinely compelling. Unfortunately, the realities of cobbling together extreme water electromagnets, powerful yet precise enough to mechanically hoist large masses of disintegrating shipwrecks from thousands of feet down, are stacked heavily against this futuristic salvage method. Number 7. Lifting wreck in parts. Imagine a massive underwater operating room equipped with intricately controlled robotic scalpels and saws. The patient, the decaying wreck of RMS Titanic. The objective, to meticulously dissect the historic ocean liner into segments and lift each section independently. However, executing the extremely precise cutting needed to slice up the fragile wreck at extreme depths pushes this salvage concept to its limits. The basic premise involves using advanced cutting tools to sever the Titanic into more manageable segments, which can then be individually lifted to the surface. In theory, sliced up in this manner, the challenge shifts from raising one gigantic wreck to raising a series of smaller chunks. But this plan critically hinges on the ability to cut the ship apart with masterful care. The remoteness and the depth of the site are the first obstacles. All cutting operations must be done robotically by tethered machines or autonomous underwater vehicles. This restricts responsiveness and physical control while introducing communication lags. The total darkness also complicates matters. External cameras light the way. The cutting tools themselves present another challenge. They must slice rapidly through thick steel, but also transition quickly to fragile areas without causing damage. A combination of specialized cutting systems would likely be needed, including large hydraulic shears, diamond wire saws, plasma torches, abrasive cutters, and more. Each has pros and cons. Perhaps the greatest challenge is choosing optimal cut patterns that section the ship without weakening it during the process or collapsing it under its own weight. The structural analyses required border on fiendishly complex due to deterioration and debris. Limited safe lift points also constrain how cuts can be made and how chunks are separated. There was an attempt to raise a small section of the Titanic's hull back in 1996, but it failed. A salvage company used a submersible vessel to attach diesel-filled balloons to the 21-ton piece, which had 4 portholes and a door. The balloons were supposed to lift the section up to the surface, where it would be taken to a museum. The company planned to raise the Titanic part by part over several years. However, the lines holding the section snapped and it fell back to the ocean floor. The operation cost $1.5 million and was a disaster. Number 6. Underwater balloons. What if the Titanic could be raised not by sturdy tanks, but by a bouquet of giant, durable balloons? This is the essence behind proposals to lift the wreck using underwater balloons or lift bags. While more flexible than rigid tanks, deploying enough balloons to raise a 46,000-ton ship still poses monumental coordination challenges. Also known as airlifting bags, these inflatable containers are designed to provide buoyancy underwater. They are often used to float sunken vessels, lost cargo, or other large objects up to the surface. The basic principle seems deceptively simple. The bags are deflated and attached at strategic points on the submerged object. Then, air is pumped into the lift bags from above. As they inflate, their buoyancy increases, and they provide lift force on the object, ultimately raising it to the surface. However, scaling this method up to work on the mammoth Titanic is an entirely different ballgame. Firstly, the wreck lies at 12,500 feet, a depth that exerts enormous pressure. The lift bags would need to be manufactured from extremely durable, flexible materials to avoid rupture. Kevlar or carbon fiber reinforced synthetics could potentially work at this depth. The bags themselves come in various designs, but most resemble giant pillows, often weighing thousands of pounds. They must include robust straps for attachment and valves to allow air to be pumped in remotely after deployment. Hundreds, if not thousands, of these bags would be needed to supply enough total buoyancy to raise the massive hull. Transporting the deflated bags to the wreck site poses logistical hurdles. Given the depth involved, this would likely require multiple support vessels, deep-sea cranes, and remotely operated underwater vehicles. Carefully placing each bag and securing it to the wreckage would be a painstaking endeavor requiring advanced robotic and navigation capabilities. Once attached, inflating the bags in a controlled sequence will be critical. Uneven inflation could destabilize the wreck, twist it, or even tear it apart due to stresses and forces applied in the wrong places. Monitoring the lift in real time and adjusting the airfill rates and sequences for each bag would require an elaborate control system. Now it's time for today's subscriber pick. Scientists' new plan to retrieve the Titanic changes everything. They propose using a massive hook to snag the liner and hoist it up whole, or surgically cutting it into sections first. As outlandish as it sounds, There are precedents for retrieving sunken ships with such extreme measures. If feasible for Titanic, we could view its iconic remnants close up for the first time. Lowering a giant grappling hook to latch onto the Titanic risks further damaging the already fragile wreck. But the hook method has raised smaller vessels. Building such apparatus on a scale to lift 46,000 tons is hugely challenging. Still, proponents argue it may be less difficult than the surgical precision needed to cut out blocks. Using advanced underwater saws to dismantle the Titanic in pieces light enough to raise allows for greater control. Though immensely complex, sectional dismantling has been used before to salvage naval warships. Once raised, Titanic's debris could potentially be restored for display in a museum exhibition. If either method succeeds for the Titanic, her rusting remnants could be restored and displayed in a museum. Visitors could behold relics of the majestic liner and her tragic demise firsthand. It would allow preserving the wreck before the ravages of time consume her entirely. However, the feasibility barriers to safely raising the decaying Titanic remain towering. What do you think? Should attempts be made to retrieve such a fragile part of history? Let us know in the comments. Number 5. Controlled explosion. Some researchers have proposed a rather explosive method for retrieving the Titanic wreck, blowing it up with dynamite. At first glance, this seems absurd and destructive, but the theory behind using carefully controlled explosions is to break the wreck into more manageable pieces for lifting while minimizing outright annihilation of the historic relic. However, executing well-calibrated blasts on a disintegrating shipwreck miles underwater is rife with unknowns. The basic premise involves strategically planting explosive charges at predefined locations on and around the wreck. By detonating these charges in a meticulous sequence, the Titanic could theoretically be fragmented into smaller chunks distributed across the debris field. These scattered sections would then be small enough to lift individually or in clusters with greater feasibility. Of course, conventional explosives like TNT and RDX are out of the question. The goal is surgical separation, not total obliteration. Specialized shaped charges would need to be custom engineered to direct and focus their explosive force with utmost precision. The charges must be powerful enough to rupture thick steel plates, but not overly pulverize the surrounding structure. Their placement and detonation sequence require fastidious modeling and analysis to minimize unintended destruction. Small mistakes or unforeseen weaknesses in the wreck could lead to catastrophic tearing or collapse from ill-placed blasts. And the underwater environment introduces unpredictable blast propagation effects. Shock waves reflect and reverberate differently in water, increasing the risks of damage. Executing the plan at extreme depths multiplies the challenges exponentially. Delicately placing charges across a massive underwater debris field demands masterful skill and exceptional technology that pushes boundaries. And monitoring the detonations in real time is critical, yet profoundly difficult. Aborting the sequence is needed if unanticipated failures arise mid-operation. While using targeted explosions to carefully fragment the Titanic for piecemeal salvage has a certain methodical appeal on paper, the realities of implementation make it a risky gambit. The variables surrounding wreck stability, blast physics, precision placement, and deep-sea operation may forever consign the controlled explosion concept to the realm of theory. Number 4. Submersible Cranes. Scientists' new plan to retrieve the Titanic changes everything. A joint engineering endeavor aims to return the Titanic to the surface using a remarkable new technological innovation, the submersible crane. This would require no ordinary marine cranes, but a new class of deep-sea giants, pushing the boundaries of engineering specifically to raise the massive Titanic wreck from its watery grave. Just operating at such extreme ocean depths, under crushing pressures exceeding 5,500 pounds per square inch, necessitates an entirely novel crane design predicated on frontier mechanical engineering and material science. Every component of the cranes, from their rigid lattice arms to their powerful electric motors to their hydraulic pumps and cylinders, must be crafted to withstand the hostile conditions of the Hadal zone. The development process draws expertise from offshore oil drilling, undersea robotics, aerospace engineering, and beyond. Electro-hydraulic control systems grant the crane's delicate but mighty articulation, while new proprietary alloys resist corrosion and metal fatigue even in near-freezing temperatures. Yet the specifications required go far beyond merely surviving at such abyssal depths. These cranes must also pack enough raw power to directly lift an object weighing over 46,000 tons, equal to the heft of over 5,000 African elephants. Some supercrane designs envision a lifting capacity exceeding 30,000 tons. That is on par with the weight of an entire Nimitz-class aircraft carrier. Integrating this degree of pure lifting potential into a deep-sea-capable crane expands the horizons of possibility. However, brute strength alone will not raise the Titanic, for she is in a profoundly fragile state of decay after 110 years on the seafloor. The once solid steel structure split in two amidships during her sinking. Her hull is corroded, her decks have collapsed, and she lies partially buried in sediment. This demands that the cranes exhibit far more than just outright power. They require delicacy and precision on a microscopic scale. The crane's attachment points on the wreckage will be crucial. Too few connections could distort or tear the vessel apart under the load imbalances, but placing them haphazardly could further crumble the surviving remnants of bulkheads and hull plates. The cranes must have a gentle but firm grip to avoid causing any further damage. Their movements and lift rates will need to be fine-tuned in real time based on sensor feedback, like a skilled surgeon operating with extreme care. While lifting the Titanic with these deep-sea leviathans could theoretically succeed based on their immense scale and power, it is their ability to combine such raw capacity with nuanced control that will determine the feasibility of raising the most famous shipwreck with the utmost care. Submersible cranes represent the pinnacle merging of ocean engineering might with a cautious precision approach, a combination that offers the profound potential to finally raise the grand old Titanic. Number 3. Hydraulic lift system. Could the same hydraulic system used to lift hundreds of tons in the industry be applied to retrieve the 46,000-ton Titanic wreck? Surprisingly, some scientists believe so. In basic principle, an array of large hydraulic jacks would be positioned beneath the hull of the Titanic and anchored to the seabed below. Thick steel plates would help distribute the lifting forces across the underside of the wreck. High-pressure hydraulic fluid, pumped down from surface vessels through reinforced hoses, would then power the synchronized extension of the jack's piston arms. In this way, the Titanic would be slowly lifted, as if on an underwater platform. But herein lies the first monumental challenge: developing hydraulic jacks capable of hoisting such mind-boggling weight under the pressures found at that extreme depth. The jacks must output lifting forces strong enough to physically overcome the inertial and frictional resistance holding down an 850-foot-long ocean liner after a century on the seafloor. That requires hydraulic cylinders engineered with the highest pressure capacities and load ratings in the world. Positioning the jacks is also critical. Too few connection points could crush sections of the deteriorating hull under concentrated loads. But ringing the entire wreckage would require a sprawling hydraulic network and invite unbalanced lifting forces. Comprehensive structural analyses and simulations would be needed to find the optimal jack placements to avoid failures. Keeping dozens of colossal hydraulic jacks synchronized in real-time miles down on the pitch-black seafloor could border on impossible. This would be an extremely complex lift evolution with zero room for error. It demands maintaining perfect harmony between the jacks to avoid structural distortions or breakages as the Titanic is nudged upward. The coordination of pressures, flow rates, and speeds is akin to a symphonic ballet, except with machines capable of crushing steel. Therefore, while lifting the Titanic through a gently rising platform of hydraulic jacks has engineering merit on paper, the technical barriers surrounding power, precision, control, and calibration at real ocean depths confine this method to the realm of theory. The risks surrounding implementing so many fine-tuned heavy-lift hydraulic systems miles deep in the hostile Atlantic may conspire to keep the legendary liner permanently grounded on the seabed. Number 2. Mass displacement. What if we could raise the Titanic not by lifting the wreck, but by making it lighter so it could float again? This is the premise behind proposals to pump expanding foam into the deteriorating remains of the legendary liner. By displacing water with buoyant foam inside the hull and compartments, the Titanic could theoretically float again. The physics behind the concept is simple. Polyurethane and isocyanurate-based foams contain inert cellular pockets that make them less dense than water. If enough of this buoyant material permeates the volumes within the wreckage, the overall density is lowered. According to Archimedes' buoyancy principle, this reduced density could provide sufficient upward force for the 46,000-ton Titanic to lift off its resting place. However, safely executing this technique on the real wreck introduces serious hurdles. Transporting the expanding foam material down to the site in the massive quantities needed already poses an enormous logistical problem. The foam components would need to be mixed and pumped through miles of heavy-duty flexible hosing robust enough to withstand intense deep-sea pressures. Installing this sprawling foam injection network on the seabed entails its own risks. Once the complex injection system is in place, achieving an ideal foam distribution throughout the interior wreckage presents the next challenge. The goal is to completely fill void spaces within the wreck without weakening her structure. But the Titanic's interior layout is a complex maze of compartments and passageways, some fully collapsed. Sonar scans and interior footage would help target foam injection points. Careful monitoring and control over the foam injection would still be needed to avoid high-pressure buildups that could rupture century-old bulkheads. As the expanding foam permeates the wreck, its buoyancy gradually increases, eventually floating the Titanic off the bottom. But this liftoff must be controlled to minimize sudden motions or snapping stresses. Crews would attempt to closely track foam volumes and injection rates and make adjustments to produce a smooth ascent profile. Other methods like pumping wax or injecting ping-pong balls have been proposed to accomplish the same goal, displacing water by filling the hull with less dense matter. However, delivering and dispersing these alternative materials pose additional problems. The wax could solidify in transit pipes, while the ping-pong balls would implode under extreme pressures. Both would face difficulties permeating the complex interior layout and fully displacing water within all the compartments and voids. Number 1. Cable lifting. Among the proposals for raising the Titanic from her grave, one of the most straightforward in concept involves cables and cranes. In this cable lifting method, powerful cranes mounted on surface ships would raise the Titanic by attaching cables to the wreck and winching it upwards. However, this seemingly simple idea faces complex difficulties in practice. To lift an object weighing over 46,000 tons from such extreme depths requires cables and cranes of immense strength and capacity. The cables would need to be made of the strongest heavy-duty synthetics, like ultra-high molecular weight polyethylene, resistant to corrosion, and capable of withstanding the pull of raising thousands of tons from extreme pressure. The surface cranes would be massive maritime salvage cranes, the largest in the world, mounted on dedicated heavy lift vessels. Yet even the sturdiest cables and most powerful cranes are useless unless the cables can be securely attached to the wreck. This presents a major challenge. The Titanic lies broken into two main sections and is deteriorating rapidly. Successfully attaching multiple lifting points on both the bow and stern segments would require advanced submersible robots and divers. The attachment points would need to distribute the lifting forces across the most structurally sound parts of the wreck. Otherwise, the Titanic's fragile state poses the risk of catastrophic failure if cables are attached poorly. Closely related is the need to carefully synchronize the lift. The cranes would need to raise the cables at identical speeds, ensuring the wreck is lifted evenly. Even minor differences in lift rate between cables could tilt the wreck or skew it under dangerous stress loads. Maintaining lift symmetry from varied attachment points on a sinking, century-old wreck requires real-time monitoring and adjustments. Thanks for watching, and we'll see you in the next one.